Hello, this is Mr. Brooks, and welcome to Lesson 6.3, proving that a quadrilateral is a parallelogram. In this lesson, we're going to try to determine whether a quadrilateral is a parallelogram. How do we prove something's a parallelogram? You got to show that both pair of opposite sides are parallel. Our first theorem in this lesson states, if both pair of opposite sides of a quadrilateral are congruent, then the quadrilateral is a parallelogram. So, we're given that both pair of opposite sides are congruent. We got to try to prove it's a parallelogram. How are we going to do that? Well, we got to get both pair of opposite sides parallel. First, it's going to be easy to say that segment XZ is congruent to segment ZX by reflexive. So then your triangles are going to be congruent by SSS. Well, by CPCTC, we would be able to say that the angle WZX is going to be congruent to angle YXZ by CPCTC. And if that's true, then the top is going to be parallel to the bottom by, if alternate interior angles congruent, then parallel lines. Then we do the same thing for the other two sides. First, we would state that this angle is congruent to this angle by CPCTC, and then this side is going to be parallel to this side by, if alternate interior angles congruent, then parallel lines. So now we got both pair of opposite sides parallel. Therefore, WXYZ is a parallelogram by definition of a parallelogram, a quadrilateral with both pair of opposite sides parallel. Our next theorem states that if both pair of opposite angles of a quadrilateral are congruent, then the quadrilateral is a parallelogram. We'll look at a proof of this in our homework, but for right now, make sure you understand that, again, if both pair of opposite angles are congruent, then it's got to be a parallelogram. Theorem 6.7 states that if the diagonals of a quadrilateral bisect each other, then the quadrilateral is a parallelogram. Again, how do you show a figure to be a parallelogram? You got to get both pair of opposite sides parallel. Then the figure is a parallelogram by definition of a parallelogram. So let's take a look at a proof of this. First, we're going to look at these two red triangles. If we can get the two red triangles congruent, then we're going to be able to say that these two outside if we can get the two red triangles congruent, we'll be able to say that these two angles are congruent by CPCTC. Then these two sides will be parallel because if alternate interior angles are congruent, then parallel lines. So how are we going to get the two red triangles congruent? First thing we're going to say is that BE is congruent to DE by definition of segment bisector. It says these two bisect each other. So also, this side is congruent to this side by definition of bisector. Then, of course, we can say these two middle angles are congruent by vertical angle theorem, VAT. So the triangles are congruent by SAS, and then we can say that, again, these two angles are congruent by CPCTC, and those sides are congruent because if alternate interior angles are congruent, then parallel lines. Now I use the exact same argument on the purple triangles. This side is congruent to this side by definition of bisector. That's congruent to that by definition of bisector. Your angles in the middle are congruent by VAT. Triangles are congruent by SAS. And so then you're going to be able to say this angle up here congruent to this angle down here by CPCTC, and then the top is parallel to the bottom by, if alternate interior angles are congruent, then parallel lines. Now we've got both pair of opposite sides parallel, so the triangles are congruent, then the quadrilateral is a parallelogram by definition of parallelogram because both pair of opposite sides are parallel. Our last theorem in this lesson states that if one pair of opposite sides of a quadrilateral are both congruent and parallel, then the quadrilateral is a parallelogram. Let's take a look at what this means. In this quadrilateral, that if the top and the bottom are both parallel and congruent, then this figure must be a parallelogram. If you got one pair of sides that are both parallel and congruent, the figure has to be a parallelogram. In example 1, it asks us, what must be the value of x in order for this figure to be a parallelogram? Well, we know that if a figure is a parallelogram, the diagonals have to bisect each other. So in this problem, you're going to have to figure out y before you're able to get x. Pause the video for a minute while you try to figure out y. To get y, you're going to set 2y minus 7 equal to y plus 2. So the first thing you're going to do is subtract the y from both sides, and you'll get y minus 7 equals 2. Then you're going to add 7 to both sides, and so y equals 9. Once you get y to equal 9, then you're going to solve 3x. You're going to set 3x equal to y. So 3x has to equal 9, divide both sides by 3, and x has to equal 3. So x has to be 3 for this figure to be a parallelogram. In quick check number 1, they're asking you to figure out the values of a and c. Well, for a, you know that consecutive angles of a parallelogram are supplementary. So we are going to have to set a plus 40 plus a equal to 180. Again, consecutive angles of a parallelogram are supplementary, which is the same as saying if the lines are parallel, then your same side interior angles are supplementary. Same thing. So now to solve this, you combine your like terms, subtract 40 from both sides, and 2a equals 140, so a equals 70. To get c for this problem, you're going to set 3c minus 3 equal to c plus 1. Subtract the c from both sides. 2c minus 3 equals 1. Add 3 to both sides. 2c equals 4. So c has to equal 2. And there's our two answers. In example 2, they're asking us to show that, see if we can determine whether these figures are parallelograms or not. In part A, they give us all three pair of angles are congruent. So right away we know if opposite angles are congruent, it's got to be a parallelogram. So we can see angle A and angle C are congruent. And then when we add up the one arc and the two arc, we get this big angle has got to be congruent to this big angle, because one arc and the two arc has got to equal the blue arcs. So yes, because both pair of opposite angles are congruent, this figure has to be a parallelogram. In part B, however, we know that if opposite sides of a parallelogram are congruent, then the figure, or excuse me, if opposite sides of a quadrilateral are congruent, then the figure is a parallelogram. But we cannot get that. We do know this to be a kite, but we do not know it to be a parallelogram. In quick check number 2, again they're asking us, can we prove these quadrilaterals to be parallelograms? Please pause the video while you try to figure out the answers to both part A and part B. Alright, in part A, we can see that one pair of sides are both parallel and congruent, and so of course A has to be a parallelogram, because we have a theorem that says if one pair of sides of a quadrilateral are both parallel and congruent, the figure must be a parallelogram. In part B, we know that if the diagonals bisect each other, the figure is a parallelogram, but if that is not what we have here. So we cannot determine this figure to be a parallelogram, because DH would have to be congruent to FH, and they are not congruent. And the same with GH and EH. So we do not know this figure to be a parallelogram. We will go over example 3 and quick check number 3 in class together. So this concludes lesson 6.3.